Howdy, this is your friendly neighborhood physics teacher here, and I'm about to go over 1D motion. So your test is Friday, and so going over 1D motion, you need to make sure you know the vocabulary. Vocabulary, there's not going to be straight vocabulary questions, but if you don't know what position, distance, displacement, velocity, acceleration, time, what those mean from a reference, there is a Quizlet on Schoology that you can use to help you out there. You will need to remember to how to convert units. Remember distance. Any distance displacements needs to be meters. Velocity, speed is meters per second. Acceleration is meters per second squared. Stuff like that. Need to know how to read position versus time graphs, velocity versus time graphs, even acceleration versus time graphs. You'd be able to read those, so your green sheet or yellow sheet. Be able to determine if someone is going in the positive or negative directions by context clues. If they're going forward, it's positive. Going backwards, it's negative. Up is positive. Down is negative. Left is negative. Right is positive. Stuff like that. Be able to use all formulas and the correct units of each variables. We're about to go over that and understand frame of reference. So variables. Variables are a big, big deal because variables and units can help you know what equation to use. So like if you see in a word problem, you see something that says meters, you know it's either your position or displacement. They're both measured in meters. And your VI is going to end up going to be your initial velocity. And it's measured in meters per second. VF is just your final velocity. And that's measured in meters per second as well. Delta V is just your change of velocity. That's just when you do your VF minus VI, just in a little equation. And of course, that also will be meters per second. T is time. That's measured in seconds. A is acceleration. And that is measured in meters per second squared, because the acceleration is the change in velocity. So if that's, you have your overtime. So you have your meters per second, so it just makes meters per second squared. S is speed, and that is measured in meters per second. Remember the big difference between speed and velocity is velocity has a direction, speed does not. D is distance. That's also measured in meters. And the big difference between distance and displacement has a direction, distance does not. And then these are your equations. I do think there's a mess up on the formula chart. On the third equation, second column, I think that T is missing a squared. So double check that and make sure. So the equation should be delta X equals VIT plus 1/2 AT squared. Make sure that squared is there. I think that was a mess up or a misprint. Okay, so here's understanding graphs. We're getting to the graph section. So fill out the column below. Thinking of it speeding up, slowing down, or staying constant. So it's asking for positive velocity. So if we think about our velocity, about our velocity graph. So that's velocity versus time. So we think about our velocity graph. In the positive direction, that means we're above the x-axis. So we're up here, so we're moving so it's a positive velocity. So we know that information. For acceleration versus time graph, it's also a positive acceleration. So again, we're up here. But we know accelerations are just a straight line. Your accelerations will always be a horizontal line. Now your velocity, it can be a horizontal or vertical. If you remember, your velocity slope is your acceleration. So if we have a positive acceleration, we're going to have a positive slope. So positive slope in the positive direction. So that means our velocity numbers are getting bigger the longer it goes. So that means we are speeding up. If we want to take it a step further, if we're going to look at our position versus time graph, so we're speeding up in the positive direction. So that means our time will look like that. So we're speeding up. So again, kind of break down the graphs. So a positive velocity again, so we're up here. A negative acceleration, so we're down here. Still a straight line. So we're at positive velocity, but a negative, so we need a negative slope. Negative slope points down. So our velocity looks like that. So if we have a negative slope, and so our numbers are getting smaller because that's the zero line. We're getting closer to zero. So we're slowing down. So positive direction, slowing down. So positive direction in position versus time means we're going up the graph, but we're slowing down. So we're going to start vertical and go horizontal. So remember, a quick way to glance to see if you're speeding up or slowing down. If you start horizontal and go to vertical, you're speeding up. And if you start vertical going to horizontal, you're slowing down. And we know it's in the positive direction because it's going up the graph. So again, we're going to look at our graphs. So for velocity versus time graph, it's negative, so we're down here this time. Acceleration is positive, so we're up here. So we need a positive slope. So positive slope points up, so we're going to be doing that. So it's a negative direction, so negative velocity, so we know we're below the zero line. Positive acceleration, so that affects the slope of the velocity versus time graph. So a positive slope points up. Now, to know if we're speeding up or slowing down, remember how the numbers work in the lower half. That X line is your zero line. So the numbers are getting smaller. So therefore, we're slowing down. We're just slowing down in the negative direction. So for our position versus time graph, negative direction means we're starting at the top, going down, and we're slowing down. So we need to start vertical and go horizontal. So the next one, we have a negative velocity again. So we know we're down there, but we have a negative acceleration. So we're down here. So negative acceleration is a negative slope. Negative slopes point down. So again, think about our numbers. We're going away from the zero line, so our numbers are getting bigger. So therefore, we're speeding up. Still in the negative direction, so we're still starting at the top part of the graph going down, but we're starting slow and going fast. So starting horizontal, going vertical. So we're speeding up. Had a couple people ask me what would a graph, because none of these answers are constant speed. So had a couple people in class ask me what a constant speed would look like. I'm glad to show you. So if we're going velocity, acceleration, just kind of keeping the same little thing again. So this is a velocity versus time graph, acceleration versus time graph, and a position versus time graph. So constant speed. So if you think of constant speed, the thing that should pop in your head is zero acceleration. So if you hear constant speed or constant velocity, you should think zero acceleration. So there's two ways this graph can go. If you have zero acceleration, because it doesn't tell you if it's positive or negative, it could be a straight line in the positive direction. It could be a straight line in the negative direction. It could be either one. And I'll do this in a different color. It could be either one. Now, if it's a straight line in the positive direction, you have a positive slope for your position versus time graph. So your graph looks like that. So the negative version, you have a negative slope. So it goes down. So that's what constant velocity looks like. There we go. Woohoo! So a person walking north at a constant speed. And we're going to draw drawing our graphs. So a person walking north in a constant speed. So north is a positive direction. Remember, constant speed. So positive direction, constant speed means we have a straight line. If we have a constant speed, we have a zero acceleration. And then to show for a position versus time graph, your speed is your slope. And so to have a positive slope, you just have a diagonal line going up. For a person standing still, so again, you have your three graphs here. So a person standing still. So that means your position is not changing at all. So to show no changing in position, you just do a straight line. That's a horrible straight line. Let's try that again. Just do a straight line. And for a position versus time graph, your slope's velocity, well, that's a zero slope. So straight line. And if that's a straight line at zero, that's a straight line at zero. So that's one of the easier ones. So a person walking south, then back home. So this one can be taken a couple of different ways because it doesn't specify if it's accelerating or not. And I realized that after a couple of questions. So this one could have two different ways. So a person walking south, then back home. So if we clear that this place, that is home. So walking south would be going down and then back home. So that just means the person is walking at a constant rate. Bless me. Walking at a constant rate and then walking at a constant rate home. So your velocity, so it's a negative direction constant, so it would be here, and then it would be here. So it's still constant, so it'd be 0 there. Now, if you're saying that it could look something like this. So that's saying that the person is slowing down and then speeding up. So your velocity is in the negative, slowing down, and then speeding up. So your graph is going to look something like that. And so you have a positive, or that's a complete, positive slope. So positive acceleration. There could be one more. This one's a little unlikely, but it technically could be. You could have something that looks like jump, something like that. This is that you are speeding up in the negative and then slowing down. So it would look something like speeding up and then slowing down. Look something like that. And those are both negative accelerations. So it would look something like that. So you had a couple of choices to pick. I was leaning more towards the pink or the white. The green is an option, but it's not necessarily a reasonable option because anytime you try to turn around, you're going to have to slow down instead of speed up. So a person accelerating north. So again, this one isn't that, this is a little too broad. I understand that. So I will give you all the potential options. So if you do it, you can't be like, I think I did it wrong. No, you probably did it right, just very broad. So north means positive, and you're accelerating. So it doesn't say if you're accelerating in the positive or negative fashion. So your velocity, since we're positive, are up here. So it could look like that. You're accelerating in the positive fashion. Or it could look like that. You're accelerating in the negative fashion. So your green would look like that. Your red or pink would look like that. So what your position versus time graph, so positive direction, so you're going up the graph, and the pink is speeding up. So you're starting horizontal, going vertical. Your green is slowing down. So starting vertical, going horizontal. So you have two options for that. So there we go. That's your graphs. So hopefully that helps understand graphs a little bit better. We're going to go into a few more details, but that's the big thing. So how do you find velocity? How do you find velocity in a position versus time graph? That would be your slope. How do you find acceleration in velocity versus time graph? Again, that is your slope. So what do you think happens in the graph below? Make up a story. I will let you make up a story, but we'll break down each one and kind of tell you what's happening during a velocity versus time graph. So the first little bit here, your first little bit here is you're at 0, right? So you have no acceleration. So you're not moving. So you're You're not moving. Then you start going in the negative. So you're moving in the negative direction and your numbers are getting bigger. So you're speeding up. In the negative direction. So then your numbers are starting to get smaller, but you're still in the negative direction, so you're slowing down. In the negative direction. Right here, that little blip right there, is where you're turning around. You have turned around. So that little blip right there, you have turned around. You're now officially going in the positive direction. So you're now moving in the positive direction, and your numbers are getting bigger, so you're speeding up. So speeding up in the positive. So right here, we're in a velocity versus time graph. So you're still moving, you're just moving at a constant rate. So it's constant. You're still in the positive, so you're still positive. But it's a constant velocity. So our last little bit here in the positive. So you're still positive, but your numbers are getting smaller, so you're slowing down. Again, right here, you're turning around because you're crossing that X line. So we've now officially gone into the negative. We've officially gone into the negative. Our numbers are getting bigger, so you're speeding up. But remember, you're in the negative now. Right here, your numbers are getting smaller, so you're slowing down. Still in the negative. Didn't mean to do that. Come back. There we go. We have a flat line, so we're at constant velocity again. Still in the negative direction. And our last little bit, our numbers are getting smaller, so we're slowing down. And we're still in the negative direction. And this is a velocity versus time graph. So kind of understanding what that graph would look like. If we wanted to make a position versus time graph, I'm not going to worry about the seconds. But so we're not moving. So we're starting, I'm going to go negative. So for first little bit is we're not moving. Then we are speeding up in the negative. So we're starting horizontal, going vertical in the negative direction. And then we're slowing down. So still going down. We're starting to go horizontal. We're turning around and speeding up. Then we're going constant. So a straight line. And then we're slowing down. So we're starting to go more horizontal. We've turned around. We're speeding up. We're slowing down, going at a constant rate, and then we're slowing down. So it looked kind of something crazy like that for your position versus time graph. If we did our acceleration, I'm just going to do it up here so I can still see the graph. So an acceleration versus time graph. So not moving, so no acceleration. So that would be a negative slope. That's all a positive slope. That's a zero slope. It's all a negative slope. Positive slope. It's a positive slope. Oh. Little tiny zero slope. Another positive slope. So it looks something like that. And it's okay that it's all jumpy like that, because it's just showing you, you're just thinking about slopes. All you're doing. So this is just so your acceleration is just telling you if it's a positive or negative slope. So now we're getting into the math part. So Ben Russian is waiting at a stoplight. When the light turns green, Ben accelerates from rest. So that is a given. From rest at a rate of 6 meters per second squared for a time 4.10 seconds. So if we're going to write down our givens. So the first thing is from rest. So that is telling us that our initial velocity is 0 meters per second. The 6 meters per second squared is telling you that's your acceleration. The t, or the time, is telling you that is your t. So those are all the givens you can pull from your question. In this case, our unknown is our displacement. We need that in meters. So for our equation, you can look back at our equations and see what equation has initial velocity, time, acceleration, and your delta x. If you look back, you'll see that your delta x equals VIT plus 1/2 a t squared. So there we go. So now we just gotta plug in. So we have 0 times 4.1 plus 1/2. Our a is 6. Our t again is 4.1 squared. We're looking for our delta x. At this point in time, you just pull out your handy dandy calculator and let the calculator do the work for you. So 0 times anything is 0. And then you can literally just plug that. So if this goes, that goes to 0, so that can go away. So then you can literally just plug this straight into the calculator. If you do 1/2, I'd put a parentheses around it, times 6 times, I would do parentheses, 4.1 squared. That's how I'd plug it into the calculator, straight like that. So you get 1/2 times 6 times 4.1 squared, and you get that your delta x equals 50.43 meters. And that is your answer. The next question is you're looking for your final velocity. And that should be in meters per second. And so now we have our distance and we have everything else. So we can almost use any equation we want to find our final velocity. The one that always pops into my head is final velocity equals initial velocity plus AT. So our final velocity, that's what we're looking for. Our initial velocity is 0. Our acceleration is 6. Our time is 4.1. So now you just have to do 6 times 4.1. And that gives you 24.6 meters per second. And that's your answer. I forgot to box my answer. Do-do-do-do. Do-do-do-do. There we go. Well, Ben's rushing again. So Ben Russian is speeding down I-14. He is going 40 meters per second. He sees a cop and slows down to 30 meters per second. In 20 seconds. What is Ben's acceleration? Give me a second. There we go. So a couple of givens. We have the 40 meters per second. We have that he slows down to 30 meters per second. And then we have his 20 seconds. And we're looking for acceleration. So our givens. So that 40 meters per second, that's our very first velocity. So that's going to be our initial velocity. The 30 meters per second, that's going to be our final velocity because that came second. The 20 seconds is going to end up being our time. So we have final velocity, we have initial velocity, final velocity, and time. And our unknown is we're looking for acceleration. So the equation, again, we're just going to use our final velocity equals our initial velocity plus AT. And we plug in what we got. So our final velocity is 30. Our initial velocity is 40. Plus, we're looking for the A times 20. You cannot add these two together. You have to bring the 40 on the other side. So you have to bring that 40. So you have to do minus 40. Minus 40. So 30 minus 40 gives you a negative 10 equals A times 20. It's being multiplied, so you have to divide. Now you just plug that in your calculator. Negative 10 divided by 20 gives you, well, 0.5, 1/2. So a negative 0.5 meters per second squared. And that's your answer. Now, a lot of people freak out when they see a negative. Remember, the negative just means direction. So if it's going from 40 to 30, you're slowing down. So therefore, acceleration has to be in the opposite direction for you to slow down. So yes, that makes sense. If I move your desk 10 meters to the north and then change my mind and move it 20 meters to the south, what is the distance traveled? So remember, distance. Direction doesn't matter for distance. So you just add them up. So it'd just be 10 meters plus 20 meters gives you 30 meters. But for displacement, direction matters. North means positive, so it's a positive 10 meters. Your south means negative, so it's a minus 20 meters. So positive 10 minus 20 gives me a negative 10 meters. That negative just means south. So I moved your desk 10 meters to the south. So now you need to pick up your little brother from school. You start You start heading to the school at 20 meters per second, and you realize you're going to be late. So you start accelerating at 2.5 meters per second squared for 20 seconds. How fast are you moving? So we do have some givens. Wish I would quit doing that. So you do have some givens. You have the 20 meters per second. You have the 2.5 meters per second squared, and you have the 20 seconds. So let's write out our givens. So the 20 meters per second would be your initial velocity. The 2.5 meters per second squared is your acceleration. And the 20 seconds is your time. And our unknown is how fast are we moving now, so that'd be your final velocity. So your equation is just your final velocity equals your initial velocity plus AT. We're looking for our final velocity. Initial velocity is 25. Acceleration is 2.5. Time is 20 seconds. So if you think about PEMDAS, you have to do the 2.5 times 20 first. So you get 50. So you get that your final velocity equals 25 plus 50. And then you just add your 25 to that, so you get 75. That's 75 meters per second. So you're going pretty fast. So next, if you drive your car 12 miles total during a 24-hour period and park it in the same spot each night, why is your average velocity during the day 0? So again, let's think about displacement. So if you park your car here, and you go to school, you go to work, go see a friend, but you always end up back there. Your displacement is 0. If you remember, to find velocity, it's displacement divided by time. So it doesn't matter that your time is 24 hours because your displacement is 0. So therefore, your velocity is 0. So a boat is moving at a rate of 11.2 meters per second and sees an alligator. The boat accelerates at 2.4 meters per second squared at 30 seconds. How fast are you moving away from the alligator? So let's write out our givens. So we have our initial velocity at 11.2 meters per second. You have the acceleration of 2.4 meters per second squared, and you have time at 30 seconds. And you're looking for how fast it's moving, so you're looking for your final velocity. So the equation you're going to end up using is the one we're using a lot, is your VF equals VI plus AT. So we're looking for the VF. Your VI is just 11.2 plus 2.4 times 30. Again, you have to multiply the 30 times your 2.4. So you get a 7.2, or not 7.2, 72. And you have to add that to your 11.2. And you get an 83.2 meters per second. So the distance between pitch and home, the pitcher's plate and home plate is about 18 meters. If the pitcher throws a ball at 44.7 meters per second, how long does it take the ball to get to home plate? So again, we have a couple of givens because we have numbers with units. So 8 meters, 44.7 meters per second, and we're looking for time. So our givens, we only have two givens. We have the distance between home plate, and we have the ball's velocity. And we're looking for time. There's only one equation that really works for. So it would be your velocity equals displacement over time. So we pull in 44.7 equals 18 divided by time. You never want what you're looking for on the bottom. So go ahead and multiply that by both sides. So you get, so you get t times 44.7 equals 18. We need the t by itself, so we're going to go ahead and divide by the 44 by both sides. And so you get 18 divided by 44.7, and you get a 0.4 seconds. So it doesn't take very long for the ball to get across. A dog is running at a speed of 5 meters per second and travels 20 meters. How long does it take? So again, we have our givens. Speed is 5 meters per second. Our displacement is 20 meters. Our unknown is time. So our equation is the exact same equation. We just plug in. So in this case, it's 5 equals 30 divided by t. We have to manipulate the t again to get t times 5 equals 30. Divide the 5. So we get t equals 30 divided by 5, which should give you 6 seconds. There we go. So we have Jack, Miss Heath's donkey, sees Miss Heath bringing food from a standstill, so that's a given, standstill, accelerates at a rate of 2 meters per second squared. He gets up to 5 meters per second before getting to the barn. How long does it take Jack to get to the barn, and how far from the barn was he? So we're looking for two different things. So let's figure out what our givens are. So our givens, so standstill, so we know that his initial velocity was 0. We know his acceleration is 2 meters per second squared. And we know his final velocity is 5 meters per second. And we're looking for two unknowns. We're looking for time, and we're looking for how far, so his displacement. So let's focus on the time first. So we have final velocity, initial velocity, acceleration, looking for time. We can use our handy dandy little equation here that we've been using pretty much all day. And we'll just plug in. So our final velocity is 5, our initial velocity is 0, our acceleration is 2, We're looking for time. We need t by itself, so we just divide over. So therefore our t equals 5 divided by 2, which gives you 2.5 seconds. So it doesn't take Jack very long to get to his food. Now to find his displacement. Now that we have velocity, we have all of our givens, we can use any equation we want. So let's use this one since displacement's already manipulated for us here. So our initial velocity is 0. We solve for our time, which is 2.5 plus 1/2. Our acceleration is 2, so 2.5 squared. That goes away because it's 0. So then you can just, again, plug that into your equation. Make sure you put parentheses by the around the 1/2 and the 2.5 squared. And you get that your displacement is 6.25 meters. So he ran about 6 meters in 2.5 seconds. Woohoo! So Mario is running to save Princess Peach for from 30 meters for 4.5 seconds. What velocity is Mario running at? So again, if we're writing down our givens, gives us distance, gives us seconds. Our unknown is looking for velocity. So we're just using the small equation again. So it'd be v equals delta x divided by t. We just plug in. So it's just going to be 30 divided by 4.5. So 30 divided by 4.5 gives you 6.67 when you round meters per second. So you're playing around on the elevator. You start at the first floor, go to the 5th floor, then go to the 3rd floor. When you are caught by Miss Heath, your punishment for playing on the elevator is finding the distance and displacement of your ride. Miss Heath tells you there are 4 meters between each floor. So basically, you start on the 1st floor. Oops. So you're starting on the 1st floor. Then you have 2nd, 3rd, 4th, 5th. And in between each floor, there's 4 meters. So going up, you've traveled 4 plus 4 plus 4 plus 4, or 4 times 4. So you've traveled 16 meters just going to the 5th floor. But then you didn't stay on the 5th floor. You went down to the 3rd floor. So you went from 5 to 4, 4 to 3. So that's another 4 meters. Now, remember, distance, you just add them up. Displacement, direction matters. So for your distance, you're literally just going 4 times 4 times 4 plus 4 plus 4 plus 4 plus 4 plus 4. So that's just going to end up being 4 times 1, 2, 3, 4, 5, 6. So that's just going to end up being 4 times 6, which will give you 24. So you traveled a full 24 meters. But your displacement just matters from where you started to where you finished. So you start on the 1st floor, but you ended up on the 3rd floor. So if you're doing your final minus your initial, your final was 3rd floor. Your 3rd floor is only 8 meters tall. So therefore, and you start on the 1st floor, so your initial 0. So your displacement is only 8 meters, even though you traveled the full 24. Think about when you drop something. What is the acceleration of the object? Does it change from object to object? So your acceleration due to gravity is negative 9.8 meters per second squared. It's negative because it goes down, and that's the same for every single object. So an apple falling from a tree for 2 seconds, at what is the height of the tree? So let's do some givens. So our givens here, so an apple falling from a tree from 2 seconds, 2 seconds is our time. Now it's falling, so we know that our acceleration is negative 9.8 meters per second squared, and we're looking for the height of the tree. So our unknown is our delta x, because we're just looking for the displacement. A couple of things is our initial velocity is going to be 0, because it's just being dropped. So it's just hanging in the tree, and then it started falling. So our initial velocity is 0. So the equation that we're going to end up using is delta x equals VIT plus 1/2 AT squared. We're looking for our delta x. Our initial velocity is 0. Our time is 2 plus 1/2 negative 9.8 t squared. 0 times anything is 0. So again, you just have to plug in 1/2 times negative 9.8 times 2 squared. Make sure you put parentheses around things. So you should get a delta x of negative 19.6 meters. And that negative is just telling you the apple is going down. So the height of the tree is just 19 meters tall. Okay, frame of reference. Finally getting there. We're almost done. So frame of reference. So we have same system and we have different system. Remember, same system is happening when an object is affecting you or affecting another object. Different system is when the two objects are not affecting each other at all. Not affecting you at all. So a couple of things to think about. So if we're in the same system and the vectors are in the same direction. So same system, same direction. So that means the object is like, think about a friend is pushing you in the same direction. So to figure out how fast you're going to end up adding. Please write. Thank you. You're going to end up adding. And actually, real quick, I'm going to end up flipping these. So we're just going to mark that out, that out, that out. So we're going to make this side same system. So these are going to end up being added. Different directions, so your friend is now trying to keep you from moving. You're going to end up subtracting. And whichever direction they're going is their direction. There's nothing funky with your direction here. And we're going to change this into different direction, or different system. And this is where it matters if an object is passing you or not. When I mean by you, I mean by the frame of reference you're in. So vectors going in the same direction is going to end up being flipped. You're going to end up subtracting. So you always subtract. Vectors going the different direction, you're going to always add. Now the thing is direction. That's the thing. I think y'all understand this part. It's knowing, is it positive, is it negative, is it east, is it west? That's the part that everyone kind of gets confused. So if the object is passing you, so if you're in a vehicle and a vehicle starts passing you, the object is going to, the object starts passing you. The direction does not change. So same direction as so the object's direction does not change. If you start passing an object, so again, you're in a car and you pass a car, that object's direction is going to flip. So if that object, if it says the object's heading east, you start passing it, it seems like the object's going west because you're pulling away from it. And then with these two, the direction doesn't, it just stays, whatever that object's going is going. So it's only these with your same direction, and it's if the person's passing you or you're passing the person is when you have to pay attention to the direction. That's the only time the direction does something funky. So let's look at these. So you have there we go. So we have a person who's walking on a moving sidewalk. You see these in like airports. And then the person's walking at 5 meters per second, and the accelerate and the is moving at 3 meters per second. So let's think about that. So if I was just standing off the moving, what would each one of these people actually look like they're moving? Well, the person walking would end up being 5 plus 3. So it actually looked like they're moving at 8 meters per second because the moving sidewalk is helping the person move. The person that's just standing there just seems like they're just moving at 3 meters per second because they're not moving. Now, if the person was being silly and turned around, then you would end up subtract. But same system. So same system because the sidewalk is affecting it. Same direction. So you end up adding. Same system, same direction, you end up adding. So how fast will the bike have to be moving to match the boat? So the river is going one way, the boat is going the other. So again, the river is affecting the boat. So we're same system, but different direction. So we're going to end up subtracting. So the boat is going at 22. Subtract that from 4. And you get 18 kilometers per hour. And the boat is heading in that direction. So if that is east or right, so it's heading in that direction. So the bike's got to book it to keep up with the boat. Last one. Hallelujah. So Miss Verona's brother is going on a fishing trip. His journey starts at mile marker 75 starts at mile marker 75 miles to the mile marker. Yeah, that's messed up. So he starts at the 75 mile marker. He travels 225 miles in 2 hours before he realized he didn't have an updated fishing license. He had to return to mile marker 25, where the Walmart was, and took him 4 hours. Find total distance, total displacement, your speed, and your velocity. So on this one, you really do need to draw out, kind of see what's going on. So you're starting at 75, or her brother's starting at 75 miles. He's driving 225 miles. So 225 miles plus 75. So he ends up at mile marker 300. It's because he traveled a total distance of 225 miles. Traveled 225 miles. He realized that he had to go back. So he went back to the 25 mile marker. So if he started at 30 and went to the 25, that means he traveled a total of 275 miles back. So you see how drawing it out helps? He's starting at 75. He goes at 225 miles. So 75 plus 225 gives you 30. So you know he's turning around at the 30 mile marker. It says he's traveling at the 25 mile marker. So he had to travel a total of 275 miles back. Now, total distance. Total distance, you just add up what you went. So it would just be 225 plus 275. You do not add the mile markers. Those are just placements. Okay, so you do not add those. You only add the total distance he traveled. So it'd just be 225 plus 275. And that'll give you he went a total of 500 miles. For his displacement, this is where the mile markers come into play. Because he started at these, because remember it's final minus initial. So he started at the 75 mile marker, and he ended at the 25 mile marker. So 25 minus 75 just gives you a negative 50. That negative is just telling you he had to go backwards. So even though he went all this way in the forwards direction because he had to go back to Walmart, his displacement is actually in the negative direction. For speed, remember, it's just distance divided by time. So you would do the 500. Now we got to go back up and see his total time. So it took him 2 hours. The first time. And then it took him 4 hours the second time. So you just add that up to get 6 hours. So it's just 500 divided by 6 to give you 83.33 meters per second. For your velocity, it's your displacement over time. So your displacement was negative 50. Your time is still 6. So negative 50 divided by 6 gives you a negative 8.33 meters per second. So your velocity is less because your displacement is less. So there we go. So hope that helps. I know it's a long video, but I tried to go over every single scenario that you might see on the test. I really wanted to focus in on the graphs. So if you have any questions, don't be afraid to ask Miss Verona or Miss Heath. Have a wonderful day. Bye.